So, so now let's talk about, I'm going to talk about a new paper called Eliciting Expertise Without Verification. Still, this is joint work with Schoenebeck. Okay. So I'm going to give you a brief introduction for the motivation of the problem and the statement of the problem and also our results. So when we need to perform a massive number of tasks, when we want a lot of information to make a decision, or when we want to forecast something, using the power of crowd provide a cheap and effective way. So here are several examples. In the massive open online course, we can use peer grading to grade a lot of homework. In the sharing economy environment, we can build some reputation system to elicit information from the users. And we can also outsource our tasks to the workers on the several cross-sourcing platforms, such as like the Amazon Mechanical Turk. And to give a better explanation, I will use peer grading as a running example of the whole talk. So the central problem we want to solve in peer grading is how to incentivize the students to invest efforts when they grade other students' homework. And the setting you can imagine is like every student is assigned 5 essays. And there are several naive solutions. One is we reward each student equally, and this will not work because it cannot incentivize them to invest efforts because anyhow they will receive the same rewards. And second is maybe we have a reliable TA, and then the TA randomly pick an essay, and then we compare the grades from the TA and the grades from the students. But that may be expensive, and also these spot check techniques implicitly assume that there is ground truth behind the questions, and it will not be applicable if we ask people some subjective questions. And the third is maybe we reward this student $1 if she is in the majority, and that will fail to motivate minority. And also the problematic thing is like if every student gives every student very high grades, they invest no effort, but they achieve the maximum amount of payment. And it turns out there is a very clever solution proposed in the peer prediction literature is that we can pay people a clever majority vote. So we not only pay them the agreements, we pay them this correlation thing. And according to my previous talk, you can think this correlation is that one example of the correlation is the F-mutual information I introduced before. And this idea can solve the problem of the majority vote. First, it can motivate minority because even you as a minority, even you're always negatively correlated with other people, but still, if we just pay you this amount of correlation, this absolute value of the correlation, so it doesn't matter. And also, it will avoid the our agreement thing because if you always report the same thing, you will have no correlation with other people because what you report contains no information. And in this case, if you pay people according to this correlation, you will be paid nothing. But this solution is still not perfect. Let's consider the following example. So if we want to ask people to grade their grade the essays according to the quality of the essay, and then they need to invest very expensive effort to really understand the essay and then to give us the quality of the essay. And it turns out they can use a very cheap rubrics thing. They can only grade the essay according to the length of the essay. And in this case, they do not need to spend expensive effort. And this is problematic because like in 2016, Gao Wright and Leighton Brown, they point out that previous peer prediction mechanisms fail in this case because they may avoid our agreement because our agreement contains no information, but they cannot avoid our cheap signal thing. And sometimes the cheap signal may have higher correlation than the expensive signal. And if we pay people only according to the correlation, and then they may just choose cheap signal because they're going to invest cheap cost there. And the problem is we need to break the symmetry between the cheap signal and the expensive signal. If we cannot break the symmetry, then how can we know whether they report cheap signal or expensive signal? And it seems to be impossible without any side information. So now we are ready to state our problem. So we want to elicit expertise without verification. We want to identify expertise and also incentivize people to invest expensive amount of effort. And the core challenge of this problem is like we need to break the symmetry between the cheap signal and the expensive signal. And our result is we will propose a hierarchical model for information structure based on natural assumption. I will give a detailed definition for this later. And we also propose a mechanism design framework that can encourage people to invest high amount of effort and also can identify expertise. Okay. So compare with the previous work, there is two closest previous work. One is from Pretlas et al. In 2017. So they only consider the single test setting. So single test, you can think like every student is only assigned one essay. And the student is also asked to report their forecast for how other students are going to grade this essay. And it's actually a very different model with us. And they can identify expertise, but their theory requires the number of population being infinite. And Acker et al. In 2017, they consider the multi-test setting. They consider the heterogeneous agent setting, but they do not consider this expertise identification and compensation. Basically, like in their mechanism, even if you're the expert, you may not get the highest amount of payment. And we propose additional assumption, and we can identify expertise. We only require small population, and it works for both settings. Okay, so now we're ready to talk about this idea. So in one of our previous work, we showed that most peer prediction can be understood as we pay the agent according to the amount of information they provide. And this amount of information is measured in a peer prediction way, is measured by the correlation between this agent's report and her peer's report. And anyhow, this will not work in the new setting. Like consider this case, if they report like only the cheap signal and we pay them according to the amount, they will still be paid a lot. So the important thing is we not only should pay people according to the amount, but also should pay people according to the value. So we need to estimate this unit price of these different types of information, and we should compensate more for the expensive signal, even though they have lower amount, but they have higher value. And we will pay agent according to both the amount and the value. And the problem is, first, how can we measure the value without verification? And how can we measure the quantity without verification? And the focus of this talk will be the first step, because the second step, we can just borrow the techniques from the previous literature. And for the first step, let me first ask you 3 geography questions. I think some of you already seen this before. So which state in the United States of America is the largest state by area? Great. Which ocean lies on the east coast of the United States of America? Okay. Which state in the United States of America is closest to Africa? Please not tell me the correct answer.
Me.
Okay. Okay. Okay, anyhow, the idea is like I assume the most common wrong answer will be Florida. But for the people who answer Florida, they cannot predict some people can answer Maine. But for the people who answer Maine, they know some people can answer Florida. So that is how we make this hierarchical assumption. It's like more sophisticated agents know the beliefs of less sophisticated agents. And it's also true in the peer grading case. If you already make sufficient effort to have access to the expensive signal, 5 minutes? Okay. 10. Okay. If you already make a sufficient effort to access the expensive signal, like quality, of course you already have access to the cheap signal, like length and the writing styles or grammars. And this assumption actually shows a way to break the symmetry between the cheap signal and the expensive signal. Basically, we know how to distinguish these two signals. And that is the formal definition here, is that we have like m methods, and like higher the circle is, which means it's in a higher level. And when
I have a question. Can you give some intuition about the difference between like expensive and non-expensive signal, cheap signal? Like what is?
How can we distinguish them in the mechanism?
No, just examples. Yeah, like an example.
This is not an example here. It's like in the pure grading case, for people who have access to the expensive signal, which is the quality of this, they know the people who only spend cheap signal, like the length, they know how they're going to answer the question. But for the people who only know the length of the thing, they cannot predict for the people who really estimate the quality of the essay. So that is this shows the difference between the cheap and basically the cheap signal can be predicted by other people and the expensive signal cannot. Yeah. Okay. And when you make sufficient effort to perform the method M, and then without additional effort, the methods that are lower than M will be performed automatically. Okay, so now we somehow finished the first step. I will give you a very concrete example later to see how we run it in practice. Okay, so after we estimate the value, we will assign higher unit price to higher level information. But we leave the analysis for the information cost elicitation. So basically, in our mechanism, we do not consider how to learn what is the real cost of the agents. So that will be a very interesting future direction because that will make the mechanism be more efficient. And now this is the second step to measure the information quantity. We just borrow the techniques we mentioned before. So still we use F information, the family of information measures. F is a convex function, measures the amount of correlation between two random variables. Independent means 0, very correlated means very high. Satisfy the information monotonicity. No matter what kind of strategy you apply on your information, you will decrease the mutual information. Okay, so now we are ready to state our mechanism. Okay, so we will pay each agent level by level. So we want to pay Alice. So Alice reports. So we will learn the hierarchy of the information structure from Alice peer. And after we finish the learning step, which I will talk about later, we will know which information is cheap, which information is expensive, and then we will assign lower unit price to the cheap signals. And then one thing I want to emphasize here is like when we pay them for the higher level, we not only pay them this mutual information between Alice report and the expensive signal, we only value this information again. Because consider the case, usually the writing style of this is a very cheap signal, the number of typos of this paper, because we can just use a computer to do that. And the quality of the paper is the expensive signal. But they may actually correlate it very well sometimes. So in this case, if we want to compensate the people who actually spend a lot of effort in estimating the quality, we only want to compensate for their information gain. Okay, so now we are ready to run this example, the peer grading example. So we will ask each student is assigned 5 essays, and we will ask them to provide their true opinion, their evaluation for these 5 essays. And we also ask them to provide their guess for other people. And in this ideal case, so we have 3 agents here, Carl, Kevin, and Tom. So Carl and Kevin, they really spend expensive effort to evaluate the quality of the essay. And they report their true opinion, which is left column. And for Tom, he only spent a very cheap effort to only querying the cheap signal, which is the length. And also Carl and Kevin, according to my assumption, they can predict what Tom gets, and that is a lighter column. And then, according to this report, we can see that Carr and Kevin, they can predict Tom's information. And they also agree with each other for their true information. And then we will think the Carr and Kevin's true information is the expensive one, and Tom's information is the cheap one, and we will assign proper unit price there and pay them according to this framework. Okay. So in this talk, we address a problem called eliciting expertise without verification, and we propose a key assumption that more sophisticated agents know the belief of less sophisticated agents. We use this assumption to break the symmetry between the cheap signal and expensive signal, and which allow us to distinguish them and also identify the expertise. And also, we propose a mechanism design framework called Hierarchical Mutual Information Paradigm to encourage people to invest expensive effort and also identify the expertise. And the future work, in addition to the real-world experiments, we're also interested in how can we design the mechanism to make it robust to adversary, and how to estimate the sample complexity we need to measure the information quantity, and also doing the information cost elicitation to know to learn the true cost of the from the agents and to pay them efficiently. Okay, thank you.
Any questions about the next section? Yes.
So for your hierarchical structure, you need the agents to know, you need the expensive agents to know the other cheap agents. You agents need to know what signal the other agent is.
Yeah, that's the assumption. Because they know the signal of the other.
I understand that the higher level agents are going to know what the lower level signals are.
Yeah.
But they also need to be able to distinguish the other agents, cheap signals and cheap the other agents.
No.
Does it look that way?
Speak up, please.
No, they only need to. I mean, in the example, they do not need to know when they count you chip signal. Just assuming there is a person who uses chip signal, and here we are giving information different parts.
Any other questions? Yes.
Yeah, it's nice work. I like that you've engaged with a really hard problem. I wonder if the technical part went pretty fast at the end, so I might have missed this, but are you able to deal with a setting where the weak signal is observed noisily?
Yeah.
So would that work equally well? If I don't know, if there's a distribution over things that
Yeah, somehow I made an assumption it's the weak signal can be observed noisy, but I make assumption if their correlation being sufficiently high, which means you can predict the chip signals. So in the noisy settings now they should be accurate perfectly. They just need their correlation be high enough.
So in that case, you'd report a distribution? Do you have something to report the distribution of the weak signal would give?
No, not the distribution, but still they are gas. But I just want the correlation between their gas and the true weak signal reported by the high cost agents being sufficiently high.
I think, okay, thank you. I think the rest of the questions offline. Thank you.